In our next example, we want to find the area of the region bounded by the graphs of x equal to 3 minus y squared and x is equal to y plus 1. This problem is a little bit different because now our equations are given to us in terms of y rather than given to us in terms of x. Both of these equations are now solved for x. When we look at the region, so I used Desmos to graph these functions because in Desmos you can type in an x equal equation. I want to mention that if you were trying to graph these on your graphing calculator, say you see a problem like this on the midterm exam and you're graphing on the graphing calculator, you would come into the second equation is pretty straightforward. It can easily be rewritten as y is equal to x minus 1. That could go into the graphing calculator. For that first equation, if I were to solve for just y squared, I would have y squared is equal to 3 minus x. And then if I were to solve for y, I would need to use plus or minus when I took the square root. So if you were putting this into a graphing calculator, you would actually need to enter in 3 equations. For y1, you could put in the positive square root of 3 minus x. For y2, you would put in the negative square root of 3 minus x. I will mention the positive square root will give you this half of that parabola. And when you put in the negative square root, you'll get the bottom half of that parabola. And then when you put in that third equation, y3 is equal to x minus 1, you will see this line. So if you were putting this into a graphing calculator, you would need to solve these equations for y, and then you could graph all 3 of these to see this graph. But what is important is that once you see this graph, you see, well, I have 2 options here. If I choose to draw my representative rectangles vertically, then I have to split this graph up at what looks like the x value of 2. Because at the x value of 2, the line is no longer on top. So we can see that this region is really broken into 2 pieces. It's broken into a piece to the left of 2, where to the left of 2 the line is on top of the lower half of the parabola. And then in the second region, here in red, if I were to draw a representative rectangle in that region, the line is no longer on top. Now that positive square root function is on top, and the negative square root function is on the bottom. So if we were going to deal with this rectangle in terms of x, let's write what that would look like. We're not actually going to solve it this way, and I'm going to explain why. But if we were going to look at this region in terms of x and draw vertical representative rectangles, you see how our rectangles drawn in this scenario touch the x-axis? That would mean that everything we put in the integral needs to be written in terms of x, and we need to be integrating in terms of x. So our limits need to be in terms of x. We would need to know what that x value is over there to the left, and it looks like it's an x value of -1, and it is. I'm going to use blue to represent that first region. From -1 into the x value of 2, and on that region, the line is on top, and the equation of that line is y equals x minus 1. And on the bottom of that rectangle, on the bottom of this rectangle here, is the negative square root function. So from that, we would be subtracting the negative square root of 3 minus x, and we would integrate this with respect to x. To that, we would need to add an integral for the red region that runs from 2 to looks like the x value of 3. And in that region, the positive square root of 3 minus x is on top. And from that, we would subtract the negative square root of 3 minus x, which is the function that is on the bottom. Now, this is something that we could integrate, but it would be a lot more work as opposed to, instead of us drawing vertical representative rectangles, if we drew a horizontal representative rectangle, imagine if we were to stretch this rectangle out, it would hit the y-axis. So that would mean that if I want to use a horizontal representative rectangle, I would be doing everything in this problem in terms of y. That means that when I write my limits, I need to make sure that my limits are y values, and that when I write my integral, I need to only have the variable y on the inside of the integral, and I would be integrating with respect to y. So let's see what the limits would be in this case if we were integrating with respect to y. I can see from the picture here this x value is -1. If I were to take that x value and plug it into either one of those equations, we would get the y value out of -2. Right here, this x value is 2 and the y value is 1. So we would be integrating from the y value of -2, that's the lower y value, to the upper limit y value of 1. Now on the inside of the integral, what we've traditionally been doing in a lot of these problems is top minus bottom. That's what we did when we used vertical representative rectangles. Now that I'm using a horizontal representative rectangle, I'm going to be doing right minus left. And the function on the right is the parabola, which is 3 minus y squared. And the function on the left is the line, which is y plus 1. And so this would be the integral that we would evaluate with respect to y if we used horizontal representative rectangles. So we can see that the integral written in terms of y is much simpler for us to evaluate than the one written in terms of x. So we're going to go ahead and evaluate this using a horizontal representative rectangle. So simplifying our integrand, we're integrating from -2 to 1 of -y squared minus y plus 2. With respect to y. So we get -y cubed divided by 3 minus y squared divided by 2 plus 2y, and all of this is evaluated from -2 to 1. So when we plug in our upper limit of 1, we have -1/3 minus 1/2 plus 2, and from that we are subtracting what we get when we plug in our lower limit of -2. And when we put all of this together, we are left with our final answer of 9/2.